Okay, our next speaker will be Julian Nowakowski, and he will be talking about an improved algorithm for code equivalence. Yeah, please start.
Yeah, thank you for the introduction. As Tung has said, I will be talking about the code equivalence problem. This is a very classical problem in coding theory. It has been studied since at least the 80s. But in recent years, we have seen quite a lot of interest in this problem coming from cryptography. And that's mainly due to the introduction of a new signature scheme, which is currently in the 4th round with NIST. It's called LESS, and it bases its security on the hardness of the code equivalence problem. Yeah, and since LESS might get standardized in the near future, it gets increasingly important to study the hardness of the code equivalence problem. So before I can define the code equivalence problem, let me first tell you what we actually mean by code equivalence. And to be able to do that, I first have to define what a linear NK code is and what a monomial is. So we already saw the definition of a linear NK code in Nihan's talk. But just as a reminder, it's a subspace C of fq to the n having dimension k. Or if you want to put it more constructively, it's a set C consisting of elements of the form x times g, where x ranges over all k-dimensional vectors, and G is just some fixed matrix, K times N matrix over FQ, and that's what we would call a generator matrix of the code. A monomial is a linear map Q, that goes from FQ to the N to FQ to the N, and it has to preserve Hamming weight. What does that mean? Well, first of all, linear map from FQ to the N to FQ to the N simply means that Q can be described by an N times N matrix over FQ. And preserving Hamming weight means the following. So if I take any vector v from fq to the n and apply q to it, then I want that the Hamming weight of the resulting vector v times q should be the same as the Hamming weight of v. Or stated differently, the number of non-zero coordinates in v times q should be the same as the number of non-zero coordinates in v. Let's have a quick look at some examples of monomials, perhaps the most two important examples. So first of all, we have permutation matrices. These are clearly monomials, right? If I just permute the coordinates in a vector, then I won't change the Hamming weight. And the other important example is diagonal matrices with non-zero diagonal. If I multiply such matrices to a vector, then I just scale the coordinates of my vector by these diagonal elements. And since it's a scaling by non-zero values, I also don't change the Hamming weight. Now, what makes these two examples so important is the fact that these are in some sense the atoms of monomials. So more precisely, you can quite easily show that every monomial can be actually factorized into a product of a permutation and a diagonal matrix. So generally, monomial matrices look like this example matrix Q that we have here on the screen. So basically like a permutation matrix, but not necessarily only having ones as non-zero entries, but can take anything from the finite field FQ. Okay, and with all of that set up, we can now define what code equivalence is. So we say that two codes, C1, C2, are linearly equivalent. If and only if we can write C2 as C1 times Q, where Q is some monomial. Where does this come from? Well, when doing coding theory, we're generally interested in the geometry of our codes with respect to the Hamming metric. And if we have two such codes, C2, C1, that satisfy this relation, well then they have the exact same geometry with respect to the Hamming metric because monomials preserve Hamming distances. So with respect to all interesting purposes of coding theories, such codes are basically the same, and that's why we call them equivalent. Now we can move on to the code equivalence problem. That's probably what you're going to expect. So the problem is we are given two generator matrices, G1, G2, of two equivalent codes, C1, C2, and the task is now to find a monomial Q such that C2 can be written as C1 times Q. Maybe it's important to stress that you're not promised in this problem that the generator matrix G2 can be written as G1 times Q. And in effect, if you were promised this, then the problem would be easy. Unfortunately, we're only promised this. So only given that G2 can be written as U times G1 times Q, where U might be any invertible matrix. And the fact that we have like just one equation, but two unknowns seems to be what makes the problem hard. In the last signature scheme, the problem is instantiated with the following parameters. N is either 252, 400, or 548. And the smallest number is in the lowest security level, and the highest, of course, in the highest security level. In any parameter set, k is set to n over 2, and q is fixed to the constant 127. Now in this talk, I don't want to talk that much about concrete parameters and want to talk more about the asymptotic hardness of the problem. And to keep things simple, we're going to keep the ratio between k and n fixed. We're also going to keep q fixed, and we're going to be interested in the hardness of the problem as n grows. And more precisely, I want to keep the ratio between k and n fixed to 1/2 for two reasons. The first is that's exactly what's done in less, so that makes it important in practice. But it's also theoretically very interesting because that setting is the one that we consider to be probably the hardest case of the code equivalence problem. Good, and now I can already tell you what the main result of the paper is, and that's a new algorithm for the code equivalence problem that solves it in runtime 2 to the n over 2, and it works for all q greater or equal than 7. Why is this interesting? Well, as I will show you on the next slide, this actually makes it the fastest known algorithm for the code equivalence problem in a wide range, a large regime of parameters. However, importantly, all parameters used in less do not fall into this regime. So for these, the new algorithm does not improve over the state of the art. So in particular, it does not harm the security of less in any way. And then there's also a quantum algorithm in the paper, and that achieves a runtime of 2 to the n over 3, and that also makes it the fastest quantum algorithm for the code equivalence problem. So let's compare the algorithm with the state of the art. Basically, the state of the art consists of two families of algorithms. And one is called short code words-based algorithms, and that's kind of the classical way of solving the code equivalence problem that goes back to 1982. And then there's a very new approach to solving the code equivalence problem, and that's called canonical form-based. That was recently introduced by Tung, who is sharing this session together with Edoardo Persichetti and Paolo Santini. And my new algorithm is basically an improvement of their algorithm, and I will talk a lot about their algorithm in a minute. But before we do that, let's have a quick look also at the short code words-based algorithms. Okay, so there's quite a lot of stuff going on in this diagram, so maybe let's try to break it down. So on the vertical axis, we take the runtime of these short code words-based algorithms, which we're going to abbreviate by SCB, right? Short code words-based. And we're going to divide this runtime by 2 to the n over 2, which is the runtime of the new algorithm. And then we're going to plot this on a logarithmic scale, going from 2 to the minus 100 to 2 to the 100. And now we're going to plot this as a function in n. And we do this for various values of q. And as you can see, if we take rather small q's, like 2 to the 3, and you can see that the graph decreases very sharply. So showing for q equal to 2 to the 3, the short code words-based algorithms are much faster than the new algorithm. However, if we keep increasing q, you see that these lines get less and less steep. And if we reach 2 to the 6, which is the orange line kind of in the middle, then the line is basically flat, right? So that shows for 2 to the 6, the runtime of these short code words-based algorithms is basically the same as the new algorithm. And if we keep pushing q a little bit more and go to 2 to the 7, then you can see that the line actually starts to increase. So starting from 2 to the 7 on, the new algorithm is actually exponentially faster than all the short code words-based algorithms. And if you keep increasing q even more, then you can see that the exponential growth gets even faster. Okay, so what you probably should just keep in mind from this picture is if q is large enough, then we are going to be exponentially faster than the short code words-based algorithms. Okay, now let's move on to the canonical form-based algorithms. And for that, let me give you some more background. So the very general settings is with canonical form functions. And to explain what that is, let's introduce some notation. So we're going to have a set S and an equivalence relation defined on that set, which we're going to denote by tilde. And to denote the equivalence class of some element x, we're going to put x in brackets. A canonical form function is an algorithm that has to satisfy two properties. So the first is, if I take some element x coming from our set S and put it into my canonical form function, then I want that the canonical form function outputs some x star, which lies in the same equivalence class as x. And the other property is, if I take another element y that is equivalent to x, then I want the canonical form function to output the exact same element from the equivalence class, so the exact same x star. So in other words, what we want to have is that this canonical form function basically computes like a canonical representative of the equivalence class. Maybe one example that hopefully illustrates what I mean here is, the set might be the integers, and the equivalence relation might be x and y are equivalent if and only if x is congruent to y mod 3. And then one possible canonical form function would be a function going from the integers to 0, 1, 2, where we just map x to x modulo 3. Right? If I put in any x here, then I certainly get something that lies in the same equivalence class modulo 3. And if I take like any y that is equivalent to x, I will get the exact same representative. Now, this is a very easy canonical form function, because the integers are here kind of easy to work with, but unfortunately we have to work with something more complicated. And yeah, that first appeared in this work by Chu, Persichetti, and Santini, which from now I'm going to abbreviate with CPS, that got recently published in Designs, Codes, and Cryptography. And in their setting, the set S consists of matrices, more precisely k times n minus k matrices over fq. And k and n are the parameters of the code equivalence problem. And they say that two matrices are equivalent if and only if A2 can be written as QR times A1 times QC, where QR and QC are some monomials. So maybe let's explain a bit what's going on here. Maybe first the notation. Why do we call them QR and QC? Well, QR acts on the rows of A1, right? We multiply this from the left, so we're going to alter the rows of A1, and that's why we have an R here, so this R stands for rows. And QC similarly acts on the columns of A1, and that's why we call it QC, right? C for columns. And why is this equivalence relation called LRL equivalence? LRL is supposed to stand for left-right linear equivalence, and that's basically a special version of linear equivalence for codes that we have defined at the beginning of the talk. Right? If you remember, in linear equivalence, the general setting was like we have a monomial that acts from the right and a general invertible matrix that acts from the left. What we're going to do here is we're going to remove this invertible matrix coming from the left and instead replace it also by a monomial. So we're going to have monomials from both sides, from left and right, and that's why we call it left-right linear equivalence. Now, in their paper, CPS studied this equivalence relation in the context of the less signature scheme. But initially, their goal was not a cryptanalysis, but in fact, they just tried to make the less signature scheme more compact, like they tried to reduce the signature size. And they showed if we had a canonical form function for this type of equivalence relation, then you could drastically reduce signature size in less. And you don't even need a canonical form function that works for all inputs. Instead, you only want one that works well for random input. So if I take like a random matrix A1 or A2 and feed it into the canonical form function, then I want the canonical form function to succeed with a decent success probability gamma. Let's say something like constant would be fine. Yeah. So like I said, the intention with this equivalence relation and canonical form function was to reduce signature size in less, but they also figured out that they also have a kind of surprising destructive cryptanalytic application. And that's the following result. Suppose there exists an efficient canonical form function for left-right linear equivalence that has success probability gamma, then we can solve the code equivalence problem in time, basically inverse of square root of gamma times 2 to the n half. Okay. And this result is like also the backbone of the new algorithm that I'm presenting today. So CPS also give canonical form functions, and theirs has success probability basically 1 minus 1 over q, and then raising the whole thing to the power of n minus k. Notice that if Q grows at least as fast as n minus k, then we're going to end up with a quite decent constant success probability. And if you want to use this canonical form function inside of less to reduce the signature size, then this is going to be just fine, because unless the parameters satisfy exactly this, like Q is larger than n minus k and everything works fine. And in fact, if you run the canonical form function in practice, its success probability is basically 1 for the less parameters. You basically never see it fail. However, in a more general setting, let's say where we don't let Q grow with n and k, but let's say Q may remain constant, which is like a typical setting for the asymptotic analysis of the code equivalence problem, then this success probability is going to be exponentially small, right? Then 1 minus 1 over k just becomes some constant, and then we raise it to something that is linear in n, so we get something exponentially small in n. And what I showed in the new paper is a new canonical form function, and it has a much higher success probability. In fact, its success probability is now basically 1, or more precisely, it's 1 minus some O of 1 over n, and this works for all Q greater than 7. Now, if you plug in the canonical form function of CPS into this result that we have on top of this slide, then we have this factor of 2 to the n half, and the gamma to the 1 minus gamma to the minus 1 half gives you something in general that might be exponentially larger than 2 to the n half, right? As you see here on the bottom left, gamma might be exponentially small in n, so this gamma to the minus 1 half translates to something that is exponentially big in n. And if you take the new canonical form function instead, which has success probability basically 1, then you can forget about this gamma term, right? That's just 1. And we truly end up with an algorithm that has success probability 2 to the n half. So like I said, with the new canonical form function, we really obtain runtime 2 to the n half, whereas with CPS, you might end up with something that is exponentially larger, provided that Q doesn't grow with n. And we plot here the runtime again for various fixed values of Q. And the theory tells us already, if Q is fixed, we're always going to be exponentially larger. But of course, the exponential growth strongly depends on Q. Like if Q keeps increasing, the exponential growth becomes less and less. But if whenever I keep Q fixed and let n grow to infinity, then the gap between like the vertical axis and the graph might get arbitrarily large. Yeah, and what's also interesting to see in this picture is you can actually see here why the new result doesn't threaten less. So the less parameters basically lie on the blue line, but they use n that are smaller than 1,000. So the blue line is invisible there, showing there we don't improve. But like I said, asymptotically, it's really an exponential improvement. Okay, let's spend the last few minutes of the talk maybe with a few technical details. So you have seen this constraint Q greater or equal than 7 now on 2 slides, I think. And yeah, that's like a requirement that the new canonical form function has. And I think it would be nice to explain where that comes from. And to do that, we have to look into the proof of this theorem where I showed that the new canonical form function has success probability basically 1 whenever Q is greater or equal than 7. So the very rough idea of the proof is, say we sample a matrix uniformly at random, having k rows and n minus k columns. And now we're going to be interested in the probability that 2 rows in this matrix are identical up to permutation. And like the bulk of my paper, that's like really a whole section in the paper, is showing this third point on this slide, so that the new canonical form function has success probability basically 1 minus p. Of course, I can't explain that here, but I invite you to read this in the paper. But let's assume this is true, and hope you believe me. And now to determine the success probability of the canonical form function, we just have to compute a bound on p, right? An upper bound on p. And to do this, I used a result by Richmond and Chelit from 2009 that was published in the Electronical Journal of Combinatorics, and they showed if we sample two vectors v and w from fq to the n minus k, then they are identical up to permutation with probability basically n minus k to the 1 minus q half. So that gives us a bound on our probability p. I'd now just take a pair, a union bound over all possible pair of rows, of which we have at most k squared. And then we get this bound that k squared is, p is at most k squared times n minus k to the power of q minus 1 half. Now, as I said in the beginning, we're going to be interested in this setting where k is n half, and then both k and n minus k simply become a theta of n. So we can rewrite the whole thing like that. So we get an n to the square, n to the 2 plus 1 minus q half, and then you can rearrange terms and easily figure out that this is the same as n to the 5 minus q half. Now the thing is, if we plug in various values of q, like say we plug in something that is at most 5, then this term is going to grow at least as fast as a constant, and in fact for q strictly smaller than 5, this even goes to infinity. And only if we go to q greater or equal than 7, this gives us something that converges to 0. So this might give the impression that this bound q greater or equal than 7 is merely a proof artifact, right? We just show an upper bound on the probability and show, okay, if q is at least 7, then this upper bound quickly goes to 0 and everything is fine. But of course, this doesn't rule out that everything stops working as soon as we have q equal to 5. And turns out that is actually the case. So let's have a look at a few concrete success probabilities in practice. See, for 2 and 3, it really doesn't work. So here it's not a proof artifact. So here the canonical form function just has success probability 0. For 4, it first looks kind of nice. So if we take like n equal to 50, then you have a success probability of roughly 50%. So it seems like okay. But then you can see it decreases as we keep increasing n, and as soon as we reach n equal to 100, it's actually 0. But it turns out for all q that are at most 5, it does work, which is kind of nice. Because there's a very nice algorithm which is called the support splitting algorithm. That's a whole different algorithm for solving code equivalence. And that can sometimes solve code equivalence in polynomial time. And in particular, it can solve random instances in polynomial time whenever q is 2, 3, or 4. So these first 3 lines are not really interesting for cryptography because we can solve them anyway. So maybe we can forget about them for our canonical form function. In cryptography, we mainly start caring about q at least at 5. And for these, everything works. So it seems, at least in practice, the canonical form function works very well for all cryptographically interesting settings. The only thing that's maybe not so nice is we can't prove it for q equal to 5, right? But that's really like the only thing that's missing in the proof. Everything else is basically there. Okay, and that already brings me to the end of the talk. So let me just summarize what I just said. We're having a new algorithm for code equivalence that has runtime 2 to the n half. If the field size is large enough, let's say at least 2 to the 7, then this is an exponential improvement over all short coast-worst-based algorithms. It's also an exponential improvement over CPS whenever q is constant, but importantly, the parameters of less are not affected. And the core ingredient is, of course, the improved canonical form function. And the previous canonical form function required q to grow as large, like at least as fast as n, and we could improve this going down to just q greater than or greater or equal than 7. And maybe let's end with a quick outlook and a potential application. Like I said, canonical form functions can not only be used in cryptanalysis, but also in constructive cryptography. And since the new canonical form function now allows to use much smaller q's, like q equal to 7, one might try to use this canonical form function inside crypto systems that and try to make them more efficient by using smaller q. Okay, that's everything I wanted to say. Thank you very much for your attention.
Question for the speaker? Please.
You mentioned before that you also gave a quantum algorithm for code equivalence. Can you briefly explain how it works?
I can try. So I didn't mention anything about the details that are behind this theorem, right? And I just used this as a black box. But this is basically a meet-in-the-middle algorithm that uses the canonical form function as a subroutine to identify matches between the two lists that you would have in the meet-in-the-middle algorithm. And then you can do standard techniques for meet-in-the-middle algorithms to improve the half in the exponent to a 1 over 3.
So it somehow comes from Grover and
Yeah.
finding collisions.
Yes, you would in meet-in-the-middle you would have two lists of size 2 to the n half, and then you would go to list of 2 to the 1 over 3, and then Grover still helps you find them.
Okay, thank you.
Any other questions?
Can you come back to the one of the final table where you look at the size of Q and the percentage of success? Yes.
Yes.
This is the when Q is equal to 5, it looks like it's working. When it's 4, it looks like it's decreasing. Did you explore after 100, or do you have a hint of what is happening?
So I can actually prove that it must fail for 4. That's not in the paper, but I figured that out while preparing these slides. So 4 definitely will converge to 0. For 5, I still don't know how to prove it, but I went to, I think, like 200, and it still was always 100%.
Any other questions? Maybe I can ask one quick question. So I wonder, like, what's the bottleneck for like having this constraint for field size? Like, well, of course I know your approach very well, so I know like how failure can happen. Like maybe it's because you're comparing the columns, or like what's the bottleneck for like for you to set this constraint on field size, like it must be greater or equal to 7. Yeah.
So you're asking why we're having this constraint on the field size?
I mean, well, I know, for example, there can be failure when you compare, for example, columns. Then, for example, if that can be removed, can we prove for like smaller field size also?
You mean if we have a canonical form function that doesn't crash even though we have two columns that are basically the same?
Yeah. I wonder where the bottleneck is.
So I played a bit with my Python implementation, and I have something that seems to work for all queues, but I have no idea how to analyze it. That's like completely ad hoc, and there are so many dependencies in probabilities. I mean, heuristically it seems to work, but no idea why, really.
Okay, thank you. Okay, let's thank the speaker again.